Okay, so the last part, I told you about the overview of what people want and what an alternative fuel would have to satisfy. And some of the qualities that you need in a fuel have to do with its chemistry, the chemical reactions of the fuel. And so now I'm going to talk a little bit about the chemical reactions for a while. And that's actually going to be a major topic later in the course, too. So, but here's the basics. So the key thing to understand is that the reactions do not occur the way you write it down. So you would normally write down fuel plus oxygen is equal to CO2 plus water. And that's the overall process. But the actual sequence of what happens is way more complicated. It might be 20 or 30 individual steps, each with their own rates, and sometimes interfered with by some other reactions, and quite complicated sequence of things. So we have to keep it straight in our mind between the overall process, which is definitely making carbon dioxide and water, and the microscopic process, which is not going that way very directly at all, very indirectly getting there. And most of the reactions involve free radicals or atoms reacting with the molecules, with the fuels, and with the bigger molecules. And this makes it very challenging because the free radicals and the atoms, the concentrations of them are very, very tiny. They're hard to detect, and also they react very fast, so they have very short lifetimes. And so that has impeded the progress in understanding this for a long time, is because it just makes it very experimentally difficult to know what's really happening. The major species you can see, like the fuel and the oxygen, are basically doing nothing. They're just sitting there. And all the action is these little transient species that you can hardly even detect. So for example, hydrogen plus oxygen, just a simple one. All of you know the overall reaction, just burning the hydrogen oxygen to make water. But you actually need at least these 10 reaction steps shown here in order to model the actual behavior of what's happening and to explain it. And the hydrogen and the oxygen actually do react in the first step. And they make H atoms and they make these HO2 radicals. But this is a very slow reaction, and this is not going to consume very much of the hydrogen and oxygen. What happens is once you've made the H atoms react with the oxygen very fast, and sometimes they make OH and O. The OH reacts back with the hydrogen even faster, and then you finally make the water, and it makes another H atom. And so then you get these chains of reactions where once you make one reactive intermediate, like an H atom or an OH radical, they'll go and do a sequence of reactions that end up making something else, and that goes on to make something else, and you get this like very, very long sequence. Maybe sort of how one guy assassinating a guy in Sarajevo in 1914 ended up getting millions of people killed in World War I. It wasn't like that guy actually killed millions of people, he just killed one guy. But it had the consequence of that because of the whole chain. So it's the same thing here, is that if this reaction happens once, that might be enough to get thousands and thousands and thousands of hydrogens consumed through these subsequent reactions. And even this sequence is not enough to explain what happens. And when people look into detail, they realize they need about 10 more reactions, which I didn't show here. So the overall kinetics are definitely not single-step Arrhenius. So in a lot of the simple CFD models, when they first started, they just said, well, we don't know what the source term is. Let's pretend the source term is just single-step Arrhenius. And then they could do some analyses, and so you have some simple formulas you get. But for any fuel, even simple fuels, hydrogen, the kinetics are definitely not that way. So the rates don't follow a simple Arrhenius law. And then to understand the A factor, the prefactor from what the overall rate is very, very difficult and complicated. And also the dependencies on the concentrations it's not just the simple, if you took an elementary chemistry book, you might think that this rate, if you doubled the amount of hydrogen, you might increase the rate by a factor of 4 because there's a 2 there. That's totally not true. So it has some strange dependence on the concentration of hydrogen and also oxygen. Actually, it also depends on the amount of water that comes in. Okay, so each of those individual elementary steps is explained by the rate law that you learned in intro chemistry. So for example, this reaction of H plus O2 to go to these guys, the rate really is some coefficient times the concentration of H times O2. So If you double the amount of H atoms, you actually double the rate of formation of OH, for example. So that's what we mean by an elementary step. This thing, K2, is called the rate coefficient. It depends on the temperature. Usually, or often, you can express it this way. It's not exactly true, but this is like a fitting formula to fit how the K depends on temperature. Sometimes the fit is too bad. And then to try to improve the fit, people put more parameters in. And so one common one is to add a T to the end term. And that makes it a little bit better. But it's still not really exactly true. So if you take the experimental points, K of T, and you try to fit them with these different forms, they don't really fit perfectly. They do generally have like a, if you make the temperature higher, usually K increases. So it has a trend like this, but the actual rate doesn't really follow this exactly. And in some cases, the K can also depend on the pressure, and that makes it even more confusing. And so a lot of effort by people like me is trying to figure out what is the true expression for the K as a function of the temperature or the function of the pressure for each of these different reactions. So there was a lot of reactions, right? I saw in that first one here. So there's 10 here, and there's actually 10 more. So there's 20 different Ks that I would like to know. And each of those has a different dependence on temperature and pressure. And if I knew all of them, then I could write down the rate law, the source term, in order to do a hydrogen-oxygen model. And so there's a lot of experimental kineticists and a lot of theoretical kineticists who work on trying to determine the Ks. And oftentimes they'll try to fit them just to these forms and figure out what the parameters are. All right, and we talk about the order of a reaction is when we double the one reactant, does the rate double, or does it go up by a factor of 4, or does it do something else? That's the order of the reaction. If it's first order, it's linear. And then the units, the rate coefficients. If you want this to work out, so that the rate, which has units of typically moles per centimeter cubed per second, and these guys each have moles per centimeters cubed, then this thing turns out to have units of centimeters cubed per mole per second. Kind of a weird unit. And that's for bimolecular reactions. For unimolecular reactions, it's just per second, which might be more obvious. Okay. Now the net rate of local change in concentration, the source term, is due to reactions, and then it's also the terms due to diffusion, convection, all this stuff. And so what I'm going to talk about exclusively is about the rate due to the chemical reaction. It's just this first term here. So I'm not going to really give you dc dt. I'm giving you just one component of it. And a lot of people call this omega. Is it you guys? Or omega dot sometimes? Yeah. In the chemical engineering school, a lot of people call this R. R of the species, like Ri. And the individual reaction, there might be many reactions which affect a species. Each of them would be an Rn. And then there's a stoichiometric coefficient. So every time, let's go back here. So this reaction here, every time this reaction runs, it consumes 1 mole of H2O2 and it makes 2 moles of OH. So the stoichiometric coefficient would be 2 plus 2 for OH and minus 1 for H2O2. So that's what these stoichiometric coefficients, the nus here, are. And there's an index for which species and which reaction, I and N. Okay. And just keep in mind, this is an algebraic equation. This is not a differential equation. Please don't write it this way. This is only true for perfectly homogeneous closed system constant volume. Unfortunately, in chemistry courses, that's how they teach it. Because I guess a lot of times they are using a beaker and it's a constant volume, basically. But it's not a differential equation. It's really just the source term. And most combustion systems are really inhomogeneous. And a lot of times they're open or have time-varying volumes in a piston. And so constant volume is definitely not correct. Also, a very important thing to keep in mind is all reactions are reversible. Chemical reactions are always reversible. So there's always a forward rate and a reverse rate. And unfortunately, many of the models that you can download off the web of fuel chemistry write some of the reactions as irreversible. They forgot to write the back part. So they only wrote the forward rate, and they didn't write this part in.
Is that because
No, in reality, they all are linked to each other. It's always reversible. And people did that, I don't know why. They were on drugs. I have no idea why they would write it that way. But it's caused massive problems because it violates the second law of thermodynamics. So you get a perpetual motion machine inside the chemistry. You can have loops that the A goes to B, B goes to C, C goes to D, D goes to A, and it just chugs around forever. And it never goes to equilibrium, and it just chugs and chugs. And unfortunately, many of the models that you would download out of a chemistry paper somewhere, somebody put some irreversible reaction in, and maybe at their condition it didn't matter, and it was fine. But then you take it and run it at your condition, by Murphy's law, 100% of the time it'll totally screw you up. Yeah?
For example, in the GRI mechanism, all the reactions are forward. But I had a problem, and I was trying to look for the reverse reaction. Is there a way that we can get that the coefficient for the reverse reaction?
Yeah, so I'll teach you how to compute what it should be. Sorry, the question was, there's a very famous mechanism for methane combustion called the GRI mechanism, very widely used, a very important mechanism. Unfortunately, when they wrote that mechanism, I think that the solver that they had couldn't handle the reverse terms. So they would write the forward reaction, and then they would write the reverse reaction as two separate reactions. In principle, this is OK. However, sometimes they forgot to write the reverse reaction. So they have some forward and some reverse, and some just forward. So the mechanism can violate the second laws of thermodynamics. Then also, as I'll show you in a little while, there's a ratio of what the rate of the forward reaction and the reverse reaction have to satisfy a certain ratio in order to satisfy laws of thermodynamics. They tried to make it satisfy it, but because they assumed certain forms of the Arrhenius expressions, it turns out that it can't quite satisfy it. So it's slightly violating the laws of thermodynamics. Now, in the case of the GRI mech, at the conditions where they did the experiments, which is a lot of conditions, it's OK. So it works OK. But, again, by Murphy's law, you'll want to use it at some condition where it's not OK. And then you'll publish it, and somebody will say, boy, that's a crazy prediction. What did you think? And then you'll realize it was all because you just cut and paste some mechanism from somebody else, and you had no idea where it came from, and it didn't actually, it didn't satisfy the laws of physics. So be warned. Another bugbear is that rate coefficients, these KFTs, are not the rates. The rates usually are these RNs, and they're not rate constants, because obviously it's not a constant, because it's a function. It depends on temperature, for example. If you want to be in the know, you call these rate coefficients. Okay? Now, unfortunately, in high school, your teacher probably called it rate constant, and it's ingrained in your brain, and you'll start calling it rate constant too. I appreciate that. They are a constant in the sense that anyone, anywhere who measures this rate coefficient should get the same number. It's a property of the atoms, of the molecules. And the atoms and molecules are the same here in Princeton as they are in Brazil or in Saudi Arabia or in Norway or wherever you happen to be making the measure of the rate constants, rate coefficients. And see, my high school teacher said rate constant too. And so they are physical constants. They're real things. They're not fitting parameters. They're real. And in fact, I'll show you from the laws of quantum mechanics, you can calculate what they are. So they're a fundamental quantity. This is also a problem in a lot of chemical engineering books and probably mechanical engineering books too. They say, I'll just use it as a fitting parameter. And so you can have any number you want as long as it fits your experiment. But of course, if your mechanism is incorrect, so for example, back here, if I tried to fit some data on a hydrogen-oxygen system using only these 10 reactions and their rate coefficients, I could probably vary the rate coefficients to make it fit my data. However, there's actually 20 elementary reactions. There's 10 more, which I didn't write down. And those are still running, even though I didn't write them down. And if I vary the coefficients of these 10 to force agreement, and basically what I'm assuming is that the other 10 have rate coefficient 0, and I manage to get a fit, almost certainly the first 10 I've done incorrectly. Because when I put the true values in of reactions 11, 12, 13, 14, 15, 16, and their true rate coefficients, which are non-zero, it's going to have some effect. And therefore, I won't fit anymore. And I only fit if I turn these back to their true values. Okay? Now, unfortunately, in the literature, many people did not get this clear in their head. And so many, many, many of the rate coefficients you read in the literature came from somebody fitting using some model, except the model was incomplete because they left out some reactions. So they're actually like glomming in the effect of all the unwritten reactions are hidden inside their fitted rate coefficients. And then when you actually go to try to measure the individual rate coefficient, you get some number completely different than literature. And then you're having like heart palpitations. You're like wondering, well, how come my number doesn't match? Right? But actually, maybe your number's true, and those guys have just made it up. But anyway, that's something to keep in mind. All right, so this is just to show how inhomogeneous the systems are. This is a model for the flame structure of a methane air flame at atmospheric pressure with GRI Mach. And you can see over the scale of, this is like tenths of millimeters, right? Yeah, each tick here is a tenth of millimeter, it's 100 microns. So the scale of 100 microns, the concentrations of species are going up and down a lot. This is a log plot. So you're getting like sort of order of magnitude changes on the scale of hundreds of microns in a flame. And so it is not homogeneous. The concentrations are wildly different in different locations in a combustion system, usually. Not always. There's some cases where you can make it really well mixed, but most of the time, unless you try really hard, it's going to be really inhomogeneous. And the temperature is also very different. So here at one side, it's like less than 1,000 Kelvin, and over here, it's 2,000 Kelvin. So that's 1,000 Kelvin is enough to make a pretty big difference in the rate coefficients. So anyway, just be warned that don't ever think homogeneous, homogeneous, single-step Arrhenius, I completely understand everything. No, completely wrong. And if you can make it fit your experiment, it means you didn't do enough points. Because if you measured a few more points, you'd realize there's no way the heck it fits such a simple rule. Okay. Many of the reactions that we care about have barriers. And so you have some molecule called AB, it's reacting with something else, C. And when they're far apart, you can model the AB as a simple little harmonic oscillator. The AB atoms are vibrating back and forth, and they bump into C. And there's some place where A, B, and C are close together. And then you have some different vibrations of this 3-atom complex. And then it falls apart and maybe makes A atom plus BC. And it has some different vibrations of BC now. So this is a very typical. You typically have a barrier to the reaction. And due to quantum mechanics, each of the vibrations has a thing called a zero-point energy attached to it. So because you can't, of the Heisenberg uncertainty principle, you can't localize exactly where an atom is and also know its momentum perfectly. The consequence of that is that there's always a little bit of energy you can't quite know what it is. And that, anyway, that energy we call the zero-point energy. It's due to the fact that the atoms are quantum mechanical. And we count the barriers from the zero-point level of AB up to the zero-point level of the complex, of the reacting complex. And that's the E0 forward. And then if you did in reverse, you get this different E0. And the difference between them is approximately the delta H of the reaction. And so if you add these two together, you should get approximately the same as that number here.
How valid is the approximation that you're making that at the transition state you can still model every reactant as a simple harmonic oscillator?
It's not that accurate. So usually the 0th order approximation is to do everything in a simple harmonic oscillator. Okay. And then the correction is they call them anharmonicity corrections, to deal with the fact that the atoms are not really moving in harmonic motions. And it's actually a big research topic right now, is how to do those anharmonic corrections correctly and easily and accurately. Not so easy to do, actually. And then another very important thing, which we'll come back to tomorrow, I think, maybe later today, is that the rate of the reaction has to do with the width of the mountain pass. So the way to think about this is that you're down in the valley, and then you have to get over the mountain pass to get over to the other valley, which I'm going to call the product valley. So I'm in reactant valley. I want to go to the product valley. There's a big mountain range in between of all kinds of conformations of the atoms which have very high energies. I just can't get there. But there's one particular conformation that's relatively easy to go through. That's my mountain pass. I want to go over the pass to get there. So I'm going uphill in energy space, up and up in energy to this one little mountain pass. And the rate's going to depend on how high that mountain pass is and also how narrow it is. So if it's a narrow little gorge, then I can't get my big army through there very fast. But if it's a big, wide, open mountain pass, then I can march 100,000 abreast through the mountain pass, and I have a higher rate. Okay, so and the rates depend on that. So and that mountain pass is sort of inversely related to the harmonic frequency of the modes orthogonal to the reaction coordinate. So you have to imagine this parabola is perpendicular to the plane of the paper. Can you imagine? Anybody of you ever been in a mountain pass? You go over the mountain pass, you're in the pass, you're just like a saddle point. On your right and your left are the sides of the mountains, right? You're up on the ridge. Ahead of you is down into where you're trying to go. Behind you is where you came from. And on either side is a high mountain. If it's a narrow pass, you can see those things are like a wall at the side of you. If you're a big broad pass, then it might be like a plane or something. And so if it's a big broad pass, then you'd have a low frequency in the orthogonal position. It wouldn't be much like a parabola at all, it'd just be flat. If it's a narrow gorge, it'll be like a very steep parabola going up on both sides. That has a big effect on the rate. So that actually controls the A factor to a large extent of the reaction. All right. Oh, sorry, this is cut off. Okay, so the temperature dependence, being like Arrhenius, comes from the Boltzmann energy distribution. So because we have to go over a barrier, only a small fraction of the collisions make a complex that has enough energy to be over the barrier. So you might have AB running into C all the time, but most of the time they're moving so slowly and they're not vibrating much, and the total energy is just not even enough to overcome the potential energy of getting up to the top of the mountain pass. So all those collisions are not going to make a reaction. And only the ones that have energies that are close to or above the barrier height are going to contribute to the rate. So because of that, there's only these Boltzmann tails of the population distribution of all the system. Only the really unusually hot ones with unusually high amounts of energy, are going to be the ones that have enough energy to react. And because you depend on how big this population in the tail is, that scales with an Arrhenius type form, because it depends on the Boltzmann fractions there. And that's where the whole Arrhenius thing comes from. And then the higher EA is, it means you're moving this to the right, you're making the tails thinner and thinner, you're getting lower and lower rates because you have lower and lower populations. All right, so how do we construct differential equations for our system? So this is without transport, it's constant volume. I'm back to the stupid chemist way of looking at it. The right-hand side is a rate coefficient for each reaction times the concentrations minus the reverse reaction, then the next one forward, reverse. Actually, where's the reverse? Anyway, yeah, this is wrong. It should be an H, I think. Anyway, so you write them just down like this, and then you write it down for every species. If you had and then you just solve for them all simultaneously. Now, you get one differential equation for every species, right? You species balance. In the CFD language, usually you do it in mass fractions of each species, yi's. So we could guys call them yi's? I don't know. And so if you think about it, you have like 6 Navier-Stokes equations to do with the overall conservation of momentum, conservation of mass, and then you'll have one of these for each species. Now, even in hydrogen, I think I already have 12 species. So I have more chemistry differential equations than I do the Navier-Stokes equation differential equations. And I'll show you later when I'm doing gasoline, I might have 10,000 differential equations because I have so many different species in the gasoline combustion. Yeah.
In that chain of reactions, like for example, the H atom appears several times.
Yep.
How are the logics of the proportion of H atom that reacts in each reaction? Like, because I don't know if the reactions take place in parallel or in series. So what is the amount of...
So you don't know. You have all these reactions happening. Many of them involve H atoms, right? 1, 2, 3, 4, 5, 6. So 6 of these reactions out of the 7 involve H atoms, if I count it right. And so for every reaction that involves H atoms, there'll be a term back in the, where I have the, here we go. So the total change of H atoms is equal to the sum of the stoichiometric coefficient of H atoms in every reaction. And so the omega involves lots and lots of reactions, so there'll be a lot of terms. And some of those reactions will be fast and some will be slow, so they contribute a lot or a little bit to the sum. Generally, before you start, you don't know which ones are important.
Well,
And
the total mass of hydrogen is conserved at all times.
the total number of H atoms in all the molecules in the system is conserved. But this is about the species H atom, it doesn't count H2, it doesn't count H2O. They also have H atoms. It turns out if you write down the rate law correctly following this recipe, it always satisfies the element conservation. But if you have a mechanism without some reverse reactions and stuff, you can actually have ones that violate that. But if you write it down correctly with reverse reactions, just by the form of the equations, it always works out just right. Just conserve the atoms. All right. Now, when I write down the differential equations this way, usually the resulting equations are what we call stiff. How many of you know what stiff is? Okay, I'll try to explain to those of you who don't know what stiff is. So the issue is the time scale. So if I have a system like hydrogen and oxygen, the hydrogen fuel is slowly oxidizing, the oxygen is slowly being consumed as the reaction proceeds. But I'm making OH radicals and H atoms, and they have lifetimes that might be sub-microsecond. So they have lifetimes like 10 to minus 6 seconds, where the oxygen and hydrogen might be living for seconds in my system. So I have like 6 orders of magnitude difference in the time scale that's important from the point of view of an OH atom. It's going to be dead in 2 microseconds. It doesn't care what happens after 2 microseconds, but it cares a lot about the details of what's happening during those microseconds it's alive. Okay? So to model it, it turns out that with the normal explicit ODE solver, you have to use a time step for the ODE solver that is small compared to the lifetime of the shortest lived species in order for the whole procedure to be numerically stable. So if I have some species that only lives a microsecond, I have to use sub-microsecond time steps when I time march in my differential equation solution. Otherwise, I'll have a numerical instability. And if you don't know what that is, I can try to show you separately. But this is a big problem because in a microsecond or sub-microsecond, the oxygen concentration is not changing at all. It's changing in the 7th decimal place, the 10th decimal place, very, very slightly. And so when I write down the terms, let's see if I can write this quickly. So I have an equation for d, the concentration of OH dt equals something. And this has a very big term, negative some k effective times the concentration of OH, because OH reacts with everything, and then plus some other little stuff about how it's being made, for example. And this number is gigantic because hydroxides react so fast. So that's why it goes away very fast. This is sort of scaled as 1 over the lifetime of the hydroxide. This might be 10 to the 6th. Okay? So in order to solve this approximately, I'll say COH at T plus delta T is equal to COH, the concentration of OH at my time, initial time, I guess T naught, plus delta T times the omega for OH, the rate of formation of OH. Okay, and this is the algebraic expression that we wrote. And in order to make this numerically stable, I want to keep this delta T short compared to the inverse of this number. So I make this number to be 10 to minus 7 seconds. But now I write the same equation for oxygen, O2. Okay. Now the rate of consumption of the OH, and it turns out the rate of consumption of the O2 in terms of moles per centimeter per second, these are the same order of magnitude. Every time I consume an OH, I make an H atom, it reacts with an O2. These are similar numbers. So if this number, this concentration of OH is very tiny. Suppose this is like 10 to the minus 9 moles per cc, something like that, some tiny number. And then I have my number 10 to the minus 7, and I have some number here. Maybe it's 10 to the minus 3. So now I have a 10 to the minus 10 plus 10 to the minus 9. I can do this arithmetic, adding 10 to the minus 10 to 10 to the minus 9, and it's OK, because the two numbers are similar magnitude. However, the oxygen is a very high concentration, so maybe it has 10 to the minus 3 moles per cc, something like that. It's much bigger. And now I do 10 to the minus 7, and this number is the same order of magnitude, so maybe it's about 10 to the minus 3. And now I'm trying to add a number that's something that's order scale 10 to the minus 3 plus 10 to the minus 10. But these guys are 7 order of magnitude different. So when you do a numerical addition of two numbers that are too disparate, I'm adding this into the noise at the edge of the significant figures of this number. Do you see the problem? Yeah, so this is like, this number is really 1.035286914 10 to the minus 3. And now I'm adding to it, 0.943 times 10 to the minus 10. And when I go this here, where's this going to be? This is the 10 to the minus 11th place. So this is 10 to the minus 3, 4, 5, 6, 7, 8, 9, 10, 11. OK, so I'm adding a number right here, 9, 4, 3. And you can see I lost the 3 is off the edge of the significant figures of the first number. You see the problem? So this problem, if you push this to the extreme, this number, the entire number can be off the significant figures of this first number. It can be over here. And what you see in your numerical solve is the O2 never changes. And so I run my combustion, I'm never consuming any O2. Obviously, something is wrong. OK? So to keep numerical accuracy, I need to make this number similar order of magnitude as this number when I add them. But that's a problem. Okay, it's not achievable if I have to keep this. I need this to be small compared to this. Otherwise, if I make this number bigger than this number, then I have a problem getting like a negative concentration, because this will probably be it's being consumed. Okay, so that's the stiffness, where the stiffness comes from. To solve this, it turns out is really hard. And nobody knew how to do it until, I think, the late 70s. A guy named William Gear figured out the first algorithm that could actually handle this problem correctly. And now there's several programs that can do it. So there's a program called DASPAC, another one Sundials, another one VODE, and there's some other ones. But these are very popular. So people in the 1980s, late 70s and early 80s worked really hard to make general purpose stiff differential equation system solving programs. And so now, those of you who know about what stiff stuff is are probably using these. And those of you who don't know what it is, I'm sorry. You're probably getting total nonsense in all your work. But now you can, basically in every combustion chemistry problem, you always have to use a stiff solver. Only if you can get away with very, very, very short time scales. So there's some special cases you can get away with it, but basically not. You basically have to make it non-stiff. I mean, you have to use a special solver that's adapted to the stiffness of the problem, because the real physical situation is stiff. And basically what we have all the time is we have one reactive radical reacting with one stable molecule. That's like the dominant type of reactions we have. That way we get a large rate coefficient, and we have a large concentration, and we only have one small concentration in the rate law, right? Because the rate laws look like K times the concentration typically of a radical times the concentration of a stable. And so if you want this, if you do this, this is big because it's a radical reacting, and this will be small. And so the total combination is small times big. If I did instead a reaction of two radicals, it would be small times small. It would be much smaller, like second order smallness. So almost all the reactions that matter of this type. This didn't come out so beautifully. Sorry about that. In the past, until the late 70s, there was no way to solve these differential equations. And so what people did was make approximations. And the most popular and successful approximation was the quasi-steady state approximation, where you go to the species like OH and say, boy, I can never solve you because your lifetime is too short. But I can make this special approximation that I can assume that in this equation, here we go. I had equation d, the concentration of OH dt. It's equal to omega of OH. And what I'll say is, well, I think the concentration of OH is tiny. So therefore, its rate of change is also going to be tiny. So therefore, I'll say this is about equal to 0. And then I have an algebraic problem. So this guy has negative some k effective times concentration of OH. And then it has plus some terms that make OH. Like, there's a rate H reacting with O2 makes OH, for example. And there's some other ones. And I'd write down all these guys and say that these guys are all about 0. And in there, then I could solve for the OH. And the solution of this would give me OH at the as given by the quasi-steady state approximation. And this works typically for all the really reactive radicals in your system. And then if you do this, you drastically reduce the stiffness of the problem. However, then it turns out it can be hard to solve the resulting system of equations because now there are a mix of algebraic equations like this. See, this is an algebraic equation, no differentials anymore because I said this was 0. And also some differentials for the other ones. So then I have to use a DAE solver, a differential algebraic equation solver. It turns out those are really hard to make them work too. And they basically didn't get fixed until the 1980s either. So people did their best they could this way. But nowadays, everybody just uses the stiff differential ODE solvers, basically. And they work great. The benefit of this is conceptually. So this approximation is actually really pretty accurate. And so if you conceptually want to know what the OH is doing, this is it. And also, if you want to check if your differential equation solver is having trouble, you can compute it by hand this way and see that the numbers better be close. If it's really different than what your numerical solution is, it means probably your numerical solution is wrong.
I was just curious if that was still, I think in classes I've taken before, the reason we learned that you would want to use that is just for mechanism reduction. Like if you have like 1,000-step mechanism or whatever and you're trying to.
Yeah, some people still do it. But then you end up with algebraic equations. So then you have to use some clever trick to get rid of the algebraic equation. If you can do that, then it still can be good. And there's some people who are really specialists in that and can do it. But I'd say if you do it and you don't know what you're doing, you're just introducing an approximation. You'll still have a hard to solve system of equations. So it's not really worth it. But sometimes it is. And for sure, it's along the right idea. And actually, Gear's algorithm is sort of based on doing this, in effect, numerically inside the code. And let's see if I can move this. There we go. So now you can see that to explain this, oops. Is that better? You can see it? OK. So to understand this, you can consider the case of A goes to B goes to C. And you can analytically solve for what the differential equation solutions are. And if we go to the next slide, this shows what it looks like, the solutions. So if the timescales for B being formed and B going away are similar, you'll make a lot of B. Okay? But if the B has a very fast decay rate, it will only go a little bit and stay very small. And so you can see its rate of change is very small because it's basically flat almost after the initial transient. And so that's the normal situation for radicals. They're like this dotted line here. And so in that limit, then you can use this equation and get an estimate of the concentration of B. And it's pretty accurate. All right, so just here's the story. Before 1980, all you could do was QSSA because you couldn't even possibly solve them. Then since the late 80s, there have been good solvers, and now you can solve almost everything. However, it's computationally intensive. So if you're doing it in the middle of a CFD calculation or something, it can be big trouble. But if you only want to solve it for one mesh element, you can definitely solve it. And the QSSA is helpful for understanding because the big numerical solvers, they give you a numerical solution, But if you have 1,000 reactions, 1,000 species, 1,000 stiff differential equations, who knows what the solution is supposed to look like? It's really hard for a human to understand it, but the QSSA you can understand. And it's basically replacing the differential equation with this equation. It turns out that for numerical solutions, it's often better just to leave it this way and let the ODE solver handle it, because those guys who developed them are very good, and they really worked hard to develop a very good method. But sometimes this is needed or beneficial, and then you can use what's called a differential algebraic equation solver. They have their own special problems, but sometimes it's good. But this is the kind of thing, it's like a specialist thing to get into. All right, next thing I want to talk about is thermo. So you all know from high school that delta G is equal to delta H minus T delta S. And the equilibrium constant is related to the standard state change of free energy. So the equilibrium constant K is given by that formula. And this K then therefore can be computed. If you look up a table, it tells you the H. And you look up a table, it tells you the S. And you compute the delta H for the reaction. And then you can compute the delta G. Then you can run in this formula, and then you can figure out what the equilibrium coefficient is. And it turns out that the reverse rate coefficient and the forward rate coefficient have to be in a ratio given by that equilibrium coefficient. Here's this detailed. So the equilibrium coefficient is defined to be the product of the activities of the products divided by the product of the activities of the reactants. The activities, for most systems, you can approximate them as the partial pressures. So the pressure over the standard pressure, or the concentration over the standard concentration. And so then you get you can plug these in and get the ratios here. This K is dimensionless, but other people use this definition, Kc. This one does not have the standard states in it. They left them out. It only has the concentrations of the species. And because of this, if the number of moles of reactants and products are different, this thing will have units that are units like concentrations to some power. And so that's when you have units here. And it turns out that at equilibrium, the reason why you're at equilibrium is when the forward rate of a reaction is equal to the reverse rate of the reaction. Therefore, K forward times the concentrations of the, it should be reactants here, sorry, and K reverse times the concentration of the products are equal. Therefore, K forward over K reverse has got to be equal to Kc by the formula here. And so knowing the Kc, which we know from the thermo, gives us a way to compute the reverse rate coefficient from the forward rate coefficient. And this property that the forward and reverse rate coefficients have to be related to each other is called the property of detailed balance. And this has to be satisfied for the laws of thermodynamics to be satisfied. So it's just, it's just sort of, this is all fundamental because it comes back from the thermo that gave you the delta G. Another just a complication that we'll come back to is the reactions of the type A plus B goes to some complex. This happens typically that A and B are molecules, are wiggling around, they bump into each other, they stick. They still have the energy that they had, so they're still wiggling around like crazy. And they also have the energy of the exothermicity of the reaction. Say A and B formed a bond. Now all that energy is in this wiggling guy. It has so much energy that it can actually just reverse and fall back apart. Because just by the way it was formed, it was above the energy for falling back apart. What it needs to do is have some collisions with the solvent or with the gas around it and give up some of its energy so it calms down, and then it'll be stable. So you need two steps. You need the A and B to bump into each other, make this energized complex, and then they have to have a collision with a third party that's going to take away some of the energy and stabilize them as AB. So the rates in principle depend on the pressure, on how much of the bath gas is around to have collisions with it to make it suck away the energy. And if we do quasi-steady state approximation on this energized initial complex when they hit each other, this is the formula you get for the overall rate. It depends on the rate of the A plus B reaction times the rate of the stabilization with the third body collision divided by the reverse rate plus this thing. And here's some examples of important cases like this, like methyl plus methyl radical. In a lot of flame systems, you make a lot of methyl radicals with hydrocarbon fuels. And then those guys can recombine to make ethane. It's a very important reaction. But that can only happen if the ethane that's formed initially, it's energized, it has to have a collision with something to take away some energy. And so you get a rate like this. So as the bath gas concentration gets very high, high pressure, then this formula simplifies. This is large at high pressure, so this is large compared to this. You can just ignore it. And then this cancels out, and you just get Ka. So what's called the high pressure limit of the rate coefficient is the normal rate you'd expect of just the, say, methyl plus methyl hitting each other. But at low pressures, methyl plus methyl hit each other, but most of the time the energized ethane just falls apart back to methyl plus methyl. And if you're watching it macroscopically, the methyls just don't seem to be going away. They can't react because when they hit each other, if the pressure's too low, there's nothing they can do and they just fall apart. And this happens like in interstellar space. There's no collision partners out there. So the things react, they hit each other, and there's no way to get up the energy, and they just fall apart. So the rates are very slow. And so in that case, you get a rate that depends on the concentration of the bath gas, of the pressure of the system. And so you can get two completely different rates. And then this gives you the general rate for the whole thing, how it depends on the pressure. And so this is the kind of thing that has saturation behavior. So the pressure's high enough, you'll get the normal rate you expected. As the pressure gets lower and lower, the rates get lower and eventually become first power in the bath gas. And the same thing happens in reverse. You can do for dissociation reactions. Another thing people do a lot is they classify the reactions. So you can classify different types of reactions. Reactions that take stable molecules and create radicals are called initiation reactions. Reactions that take one reactive species, like an H atom, and convert it into more than one reactive species, like OH and O atoms. Those are called branching reactions because they sort of create new chains of reactions. And here's another one. An O atom is one reactive species. It reacts, it makes two reactive species. And then reactions that have one reactive species making one reactive species, those are called propagation reactions. So they don't change the number of radicals in this case. And so this classification is very helpful to try to understand. When you have a very complicated mechanism, you're trying to understand what happened. If you can classify them, you can kind of consider families of reactions at a time. It helps you to understand what's happening in the kinetics. The T reaction of termination, that's when two reactive species combine together and become something that's not reactive. So for example, these two guys combine, make two stable molecules. Okay, so I take a few reactions like I had there, and then I try to predict what's going to happen. This is the ignition limits for hydrogen and oxygen mixtures as you change the temperature and as you change the pressure. And what you'll see is you have, suppose you say a constant temperature here and you change the pressure. At low pressure, it doesn't explode. Then when you get to pressures around 10 to the minus 2 atmospheres, it explodes. Then you get up to 10 to the minus 1 atmospheres, it doesn't explode again. Then when you get up to about 10 atmospheres, it explodes again. What the heck? Right? Now, all I had was those 20 reactions. They're not that hard. People have studied basically all of them. I have pretty good estimates of all the KFTs. How the heck does this happen? And it's like sort of if you have a couple stiff differential equations together, it can do all kinds of wild stuff. And each of them depends, all the rate coefficients depend on T and P in different ways. So the relative of which one's important or not important is changing as I change the temperature and the pressure. And so I can get the whole thing to behave in completely different ways. This thing called the second explosion limit, this one, it turns out you can understand it just by understanding two of the reactions. The reaction of H plus O2, let's see, I'll show you backwards. There's two H plus O2 reactions here, this one and this one with M. So now I'll go back. I wonder if I have that next here. Maybe I have it here. No. So the first one is H plus O2 is a branching reaction. And the second one was H plus O2 to M. This one makes HO2, which under those conditions is mostly all going to terminate. So this one basically kills off reactive stuff. This creates more reactive stuff. And those two guys, when they're balanced, that's right at the limit. And if you're dominating that you're killing off reactive stuff, then it won't explode. And if you're dominant that you're always making more reactive stuff, then it's going to explode. And so that's how that defines the limit. And you can see that if you just make that approximation, just consider just those two reactions, you actually get a pretty good close approximation to this line. If I add the other 18 reactions, then I actually get the line. Because they actually do something. But basically, those two reactions are the dominant ones for those particular conditions. And people spend a lot of time, and they analyze the system completely and understand what's causing this one and everything. You can look up and see about it. But it's just something to keep you in mind that although you think you understand a chemical system at one condition, if you go too far away in condition space, completely different reactions can take over and be the dominant things because they all have strange T and P dependencies on each other. Let's talk about some other important reactions. This is really curious. So in a lot of combustion systems, you make a lot of carbon monoxide. And yeah?
So why there are certain reactions do not have pressure dependence, for example, O plus H2?
Yeah, so reactions, yeah, good question. You guys see here? Okay, so you get pressure dependence when you have two molecules reacting and they make a well. So here you have this excited species that's formed initially, and then this guy can get quenched to go back, or it can go back. That's the situation. So anytime you have this kind of configuration is when you can have importance dependence on the pressure. Now if I do the other kind of reaction I showed you before, where it's just going through the barrier, this one never, this complex, the transition state, it doesn't live long enough to have any collisions. If you have enough energy that your Boltzmann tail, you can come in, it just sails through. There's a mountain pass here, you go right through the pass. You don't have to have any collision with any bath gas for this reaction to occur. So that's the fundamental. Is that good enough to answer? The story gets more complicated because this guy here, it could be like this. And then you could have a case where this guy could actually react that way too. And then you'll have, at low pressure, this is negligible, and it will just go on and make, say, C plus D. But at high pressure, this will be negligible, and it will all go down and get trapped to make AB. So then you get a pressure-dependent branching. Very confusing.
So this is H plus O2.
Yeah, H plus O2 is like this, for example. Yeah. And there's a lot of them. It's not just H plus O2. It's like so many. So my group makes very large mechanisms, maybe 10,000 reactions in the mechanisms for different fuels. Typically, about 1/3 of the reactions are very significantly pressure-dependent. And which ones are significantly pressure-dependent depends on the pressure, the temperature, how deep these wells are affects it a lot when you work out the formulas for what the rates are. So it's non-intuitive. It's kind of a complicated story. But if you do the numerics carefully out, it all makes sense, usually. All right, so what else we got here? Carbon monoxide. So you might think, and people initially did think, that if I mix up some carbon monoxide, some oxygen, I should be able to burn it to make CO2. But when they did the experiments, they had all kinds of trouble. A lot of times they couldn't make it burn, and they thought it should just work this way. The carbon monoxide should react with the oxygen and make an O atom. The O atom would stick on the carbon monoxide and make CO2. But it turns out that doesn't work. Instead, what happens is this second set here. You do get the carbon monoxide react with oxygen to make O atoms, but then the O atoms, if you have any water around, can react with the water to make two OHs. And so that's one of these reactions where I had one reactive species, one O atom, and now I've made two. So I have a branching reaction. And then the OH is very fast to react with the CO to make CO2 plus H. And this is another one of these like this. So in that case, A and B are OH plus CO. And here is H plus CO2. And there's actually a species here called HOCO, which nobody knew about for a long time. But in the last 10, 15 years, people actually detected that this is here. And if you increase the pressure enough, you'll start making a lot of HOCO. But most of the times at the conditions of the combustion experiments, you're very hot. The temperature's high. And so you're flying way over up here. You're way, way, way above there. And it just flies right through. But this is much, much faster than the other mechanism. And part of what you can see, the first mechanism at the top, the second reaction is CO plus O atom making a CO2. And so you're killing off your reactive species. So the first reaction made the reactive species, the second reaction killed the reactive species. You don't have any branching. So you only have a very, very tiny concentration of reactive species. But in the second one, every time you make an O atom, you make 2 of these reactive species, and then those guys, they don't get killed off because it makes H atoms. The H atoms react with O2 to make more. And so you keep making more and more and more reactive species. So if you have a little bit of water present, then the CO burns the CO2 very effectively. If you keep it completely dry, then the CO won't burn. All right. And these ones at the bottom here are how hydrogen burns. So that last reaction, H plus O2, so it's reaction 3.41. Do you see that? That reaction is called the combustion reaction sometimes. It's the most important reaction because almost every fuel we have has H atoms in it. And once you make an H atom, you get one free, you always have oxygen present when you're doing combustion. The H atoms react with O2 very fast. If the temperature is high enough and the pressure is low enough, the H plus O2 goes very effectively to O plus OH. And it's a reaction that takes 1 reactive species to make 2. So then you can get positive feedback. It's like every time you put a reactive species in, you get more. You get more, you get more. It's like the screech you get from a microphone when you put it next to a loudspeaker. You get positive feedback, and you get explosions. And so that reaction makes it.
You just said that that was a low pressure, high temperature dependent reaction.
Yeah.
If you were looking at, let's say, 10 atmospheres, would you consider that low pressure?
So around 10 atmospheres, you'll start to see that the temperature where this turns on significantly is, you have to go to significantly higher temperatures to make things ignite.
Okay.
So this is a big reason why when you vary the pressure, the whole thing changes. It's because it changes the temperature that you need to achieve to get this to turn on to be important.
Okay.
And so, but in your piston or something, the temperature might not change that much. So you might see that above a certain pressure it doesn't work or something.
But it's still that same reaction that's responsible for the majority of the combustion regardless of the pressure?
Yeah, unless you have very unusual systems. But as long as you're anywhere near, so above 1,000 Kelvin, this one is usually the dominant thing.
Okay.
Yeah. At all the pressures, normal pressures we'd have. And then once you get the O atoms react with hydrogen to make more OH and more H atoms. And then the OH reacts with hydrogen again and makes more H atoms. All those H atoms go back and react with O2, and they make more and more radicals, and the whole thing explodes. And so this is the explosion, is due to this. And that's in H2O2, and it's also in most hydrocarbon fuels. This is the main reaction that makes the explosion. Okay, so the main story about this is many fuels have very strange ignition explosion kinetics, which is really important because that controls the cetane and the octane number, and it's basis of fuel rating. These are some maps of the explosion limits as a function of pressure and temperature for different fuels. You can see that they're all alkanes, but they have quite different behavior with pressure and temperature. And sometimes you get weird non-monotonic behavior. It's really strange. Do you see that? Like as you increase the temperature, all of a sudden it doesn't ignite, it doesn't explode, just like hydrogen oxygen. I showed you that one where you can go different points, different things happen. So that's very bizarre. And so we'll talk in detail about why this is. This is very important for fuel combustion because the ignition delay is such an important property. And it has very curious kinetics, as I'll show you. All right, so generally what we do is we want to be able to make a model that has enough chemistry in it that it catches the important behavior of the fuel and has enough fluid dynamics in it that it captures the important fluid dynamics that affect our behavior of our device, of our engine, for example. But this is a tricky thing because, as I showed you, the fuel equations are really complicated. They're stiff, and usually there's 1,000 of them or some huge number. And as many of you know, the fluid dynamics equations are not so easy to solve either. And then you usually want to solve it in some real device that's on centimeters scale, maybe even bigger than centimeters. And so the Reynolds number is some ridiculous number. So the whole thing's turbulent. So basically, maybe just quit and go home. But we're bold, and we stick on. And so we need to figure out how we can make a mechanism that captures all the important fuel qualities, and then how to reduce that mechanism to make it something that's numerically solvable, and then how to combine it with what aspects of the fluid dynamics are needed in order to predict the real behavior of our device for the things we're trying to predict accurately. And then if we can do that, it's great, because then we have a way on the computer to figure out what engines are the best, figure out what fuels are the best, do the optimization of the whole system. If you don't do that, you have to do a heck of a lot of experiments. And the experiments are not so easy with engines or with new fuels. With the fuels, a bad thing about it is you may need to actually manufacture the fuel to make enough fuel to run your experiments. That can be a lot of money, because you have to build some chemical plant just to make your fuel you want to try. And the engine experiments are not that cheap either. So if you can do it in the computer, it's great, but you have plenty of problems with this, for sure. And so a big part of it is evaluating whether the mechanism is correct. So we have to try to write down all the reactions and have good estimates of all the rate coefficients. And then oftentimes we're not satisfied. We think our error bars and the rate coefficients are too large. And then we have to do extra experiments or extra calculations to try to improve the accuracy of those guys. And so this is often like a long loop where we'll make a mechanism, do some experiment, try to evaluate rate coefficients, figure out that we're not happy with the mechanism, go back, try again, try again, try again, until we think we have a mechanism that's pretty good for some simple situation where we can do the experiment easily. Then we'll try to marry this into the fluid dynamics to try to do the complicated system. And usually in the beginning parts, the chemists are afraid of fluid mechanics anyway, so they would just say, let's find something that's like batch reactor, quiescent system, laminar, nothing, one-dimensional, zero-dimensional, nothing complicated, because otherwise, in the analysis, you have to deconvolute how much of what you see is due to the fluid mechanical situation you're in compared to how much is due to the chemistry, which at the time you're doing this, you're not sure your chemistry is even right. So there's a whole series of simple experiments that the chemists will do over and over until those all work. Then they start to feel that their chemistry might be right. Then they'll go and try it in a more complicated system. All right. And this whole approach is for combustion, but it's the same in many things. So atmospheric chemistry, the whole story of the ozone hole, the smog problem is all about the same thing. Interstellar chemistry, there's a whole lot of people who study what happens in outer space. They do exactly the same thing. They have to combine the fluid mechanics with the chemistry. All right, so let's take a break, and I'll tell you about measurements after we break.